In LeetCode problem 27, remove element, we're asked to remove all instances of a given value from an array in place. But this isn't just an academic drill. It mirrors real-world cases like memory-tuned caches, event filters, or streaming data cleanup where minimizing overhead is key. The real test isn't just removing elements. It's doing it fast and tight. Our first thought might be to shuffle values around, but is that smart under pressure? Let's paddle in and find out. All right, ducklings, let's waddle into the brute force route, the most basic path through the pond. It's not fast, but it's methodical. Let's walk it through in code. We'll kick things off by saving the original array length so we can manage shrinking it as we go. Next, we drop in a counter to track how many valid elements we're keeping. That's the number we'll eventually return. Time to scan each element one by one and check if it matches the value we want to remove. If we land on a match, we shift every element after it one step left to overwrite the removed value. After shifting, we reduce the array's effective size, since the last slot is now irrelevant. We also roll back our index by 1 to recheck this spot. It now holds a new value that hasn't been vetted yet. If there's no match, we simply count that value as one to keep and move on. After we've reviewed the whole array, we return the count of kept values, which gives us the size of the valid segment up front. This method swims in at big O of n squared time, which means up to 100 million operations on 10,000 elements. Not great for scale. But space-wise, it's big O of 1 since we edit in place. Just beware, performance tanks fast on bigger arrays. Can we cut out the waste? What if, instead of shifting everything, we just write good values forward as we find them? Let's plant a pointer to mark where the next non-target value should go. This lets us overwrite unwanted values directly, no shifting required. Now we scan through the array, looking for values that aren't the one we're supposed to remove. If we find a keeper, we toss it into the next open spot using our right pointer and advance it. Once we're done scanning, the right pointer tells us how many values we kept, and that's our result. This method trims the fat with big O of n time, just 10,000 moves on a 10,000 element array, and keeps space at big O of 1. It's lean, clean, and duck approved. But what if we could skip even more? Instead of writing every keeper forward, can we toss unwanted values out by swapping with the end? Here we set up two trackers, one for our current position and one for the array's shrinking boundary as we remove values. We loop while our position is still inside the valid array range. That way, we only touch what's needed. If the current value matches the target, we overwrite it with the last unchecked element and shrink the valid range by 1. If it doesn't match, we just move forward, since that value's fine as is. When the loop wraps up, the current size tells us how many values remain that aren't equal to the target. This final version clocks in at big O of n time and big O of 1 space. But it shines brightest when lots of target values cluster near the end. It's fast, space-smart, and interview-ready. We kicked off with brute force, slow and steady, but bogged down by big O of n squared. Then we refined it with the in-place overwrite, a big leap in clarity and speed. But the star move came last, two-pointer swapping. By offloading unwanted elements to the end, we avoided costly shifts and made our logic crisp. This pattern is a powerhouse in systems where speed and space are critical, like caches or streaming filters. Nail this trick and you're well on your way to thinking like an engineer under pressure. So, where else could you use two-pointer overwrite to save cycles and memory? Keep coding, keep quacking, and we'll see you in the next algorithmic challenge.